let me click it.
How about now?
Okay, perfect. Yeah,
Okay.
go ahead, Andrew.
Okay, thank you. It's great to chat with everyone here about something that I've become increasingly interested in the last year or two, is temperature-related mortality. And this is some work that actually was done by my former grad student, Zhang Ho Li, who's since graduated, is now working as a postdoc at University of Illinois at Chicago. And so what we wanted to do is really try to understand this argument that's been going on. If you read Twitter, and climate Twitter, et cetera, and you see some people, here's a quote from Joe Biden saying the number one weather-related killer is heat. 600 people die annually from its effects. And if you look over on the right, that was judged true by PolitiFact. On the other hand, this is a quote from Vivek Ramaswamy. If you remember, he was running for the Republican presidential nomination last year, and he said 8 times as many people die from cold as heat. The right answer to all temperature-related deaths is, again, more fossil fuels. So, they both can't be right. Is heat the number one killer? Is it cold temperatures? And so we wanted, so I started thinking, this is something that's interesting. Let me look into the research on this. And then we found some angles that we thought we could extend. So we decided to do some work on it. And I'm going to talk about the work we did looking at temperature-related deaths in the US. And so let me talk a little bit about the approach we took. All right, so the first thing we do is we derived a historical relationship between temperature and mortality. And I'll talk about how we did that in a second. So we derived this relation. Basically, it's just a regression between temperature and how many people die. And then we take that and we apply it to simulations from high-resolution climate models of the future. And then from this, we can predict future mortality. And we can also predict past mortality. So we can predict mortality at any time using the regressions along with temperature, either observed temperatures or temperatures from climate models. And so let me talk a little bit about the data sets we're using. So when we want to derive the historical temperature mortality relationship, we take mortality data from 106 cities. You can see here they are. They basically cover the US. We're missing a little bit in the sort of the northern Midwest part. But basically reasonably well covers the US. It's 106 medium and large cities. The data come from 1987 to 2000. It's harder to get more recent data because of privacy issues. I'll talk a little bit about that later. And the mortality data are stratified by age group. So there's an old people and younger people. I think it's split at 75. And we get these data from the National Morbidity, Mortality, Air Pollution Study. So the data are publicly available. And so this gives you all-cause deaths. They've subtracted out accident deaths, but otherwise all deaths are put in there. And then we get population demographics data also from the same, they also give us population demographics data. And then for temperatures, we use daily average 2-meter air temperature from a reanalysis, ERA 5 land. And then we do is we take these and we're using kind of just a standard method that other people have done in the literature using this distributed lag nonlinear model from Gasparini. So Gasparini is kind of the gold standard of doing these estimates. We're just using his package. In fact, he has an R package that does this. And it's essentially a Poisson regression with lags. So it takes the last 21 days and does a regression on all of those temperatures and to estimate the log of the number of deaths, basically. And so we extract the temperature mortality relationship, and we do it for every city individually, and we do it for the 2 age groups, the old people and the younger people. And then what we do is we calculate what's called a risk ratio, which is the number of deaths compared to the deaths where compared to the temperature where the minimum number of deaths occur. So let me explain what I mean. So the mortality curves look like this. And this plot has temperature on the x-axis and risk ratio on the y-axis. You see it's a U shape. And there's a minimum of the U shape, and people call this the minimum mortality temperature, the MMT. And that's defined to be 1. Now, it's not 1 on this plot because we're averaging 106 cities that have different MMTs. When you do the average, your minimum actually is slightly above 1. But for any individual city, the MMT is 1. And that's the lowest, that's the temperature where you have the fewest number of deaths. As you go to different temperatures, either higher or lower, the number of deaths increase. And the fractional increase in deaths is the risk ratio. So if you come here to say 12 degrees Celsius, has about 1.1, which means you're getting 10% more deaths than you are here at 22 degrees Celsius, which is the minimum mortality temperature. Again, this is an average. Each city looks a little bit different. But this kind of tells you what we derive from the data. Now, there's a couple interesting things about this. First of all, you'll notice, and I'll come back to this, the hot side, the side of temperatures above the minimum mortality, it is much steeper than the cold side. The cold side doesn't have a very large slope, whereas the hot side really rises rapidly, which means that as temperatures warm, the number of deaths you're going to see on the hot side is going to go up very quickly. The other thing that's interesting is you'll notice that there's a lot of deaths occurring at temperatures nobody would consider cold, say 15 degrees Celsius. 15 degrees Celsius is about 60 degrees Fahrenheit. Nobody would consider that cold. In fact, I'd consider that to be super pleasant. And yet you see more deaths. I have not heard a good explanation about why you see more deaths at those temperatures. That's a really interesting question. Maybe that people know that, and I just don't know it. But it's a really interesting question that I haven't quite figured out. Why is it that you have this minimum mortality temperature around 20 degrees Celsius, and as you go even slightly below that, you see the number of deaths go up? And these are not, importantly, this is a statistical method. In fact, let me make that point. This is a statistical method. This is not an explicit cause of death. If you die when it's 65 degrees Celsius outside, or 65 degrees Fahrenheit outside, no medical examiner is going to put on your death certificate, died from cold temperatures. Maybe you had a heart attack, you had a stroke, something happened that caused you to die. It was, whatever it was probably enhanced by cold temperatures. Maybe, the chance of having a heart attack goes up very slightly as the temperature goes down. But it's not that these people are actually dying from cold temperatures. This is an excess death analysis. This is where you're looking at deaths above what would have occurred at the minimum mortality temperature. And I'm really interested in why you get this. It's not at all clear to me what's happening there. All right, so if you want to calculate future mortality, you have to ask the question, how are people going to adapt? Because people aren't just going to sit there and broil. People, especially people that have money, will take actions to deal with the warmer temperatures. And so we look at two what I consider to be bookend scenarios for how adaptation could occur. So the first one is no adaptation. This is sort of the worst case scenario where people don't do anything. And so we just take the curves we derive from historical data, and we assume for each city, those are the same curves that are going to happen throughout the future. So there'll be no change in future mortality, or there won't be no change in the curves. The only thing that's going to change is the climate will change and the demographics are going to change. The other scenario, which I think is sort of a best case analysis, is what I call high adaptation, what we call high adaptation. So let me explain just sort of conceptually what we're doing. I'm not going to go into the details. If you're interested, they're in the paper. So for the high adaptation scenario, we adopt what people call the analog city approach. So let me show you two cities, Seattle and Phoenix. And you'll see the two curves on here. And again, the red curve is for the older age group. The blue curve is for the younger age group. I need to adjust my screen. So my window is covering my screen. I couldn't see what I was doing. So these are two cities. Again, you're looking at the risk ratios. The red line is for older people. The blue line is for younger people. And you'll see that these curves look completely different. Seattle and Phoenix look different. And again, it reflects the fact that there's been an enormous investment in people adapting to live where they live. So in particular, if you look at the hot side of these curves, you'll notice that in Seattle, warmer temperatures kill a lot of people. You see the risk ratio curves go up. In Phoenix, they don't kill anybody. And again, that reflects the enormous investments in, for example, air conditioning that allow people to survive extremely high temperatures there. Whereas Seattle is not a place that's really well air conditioned. And on the cold side, you see the opposite. In Phoenix, you see older people have a very high risk at colder temperatures, while in Seattle, they're better adapted to colder temperatures. So what the analog city method is, it says that if the summer climate in Seattle warms to be where Phoenix is today, then the temperature mortality relationship in Seattle will be like today's Phoenix. So as Seattle warms up, if it gets to the temperature of Phoenix, its curves will look like Phoenix. And again, this is a sort of a best case scenario. It's hard to imagine that you'd ever be better adapted than Seattle. And it's easy to imagine that you don't do that well. As anybody who lives in Texas knows, air conditioning is expensive. Installing air conditioning is expensive. Fixing air conditioning is expensive. Running your air conditioner is expensive. A lot of people simply can't afford that. And so it's easy to imagine that these people aren't as well, will not be as well adapted in Seattle as they are in Phoenix today as the climate warms. Rich people certainly will, but lots of people are not. In fact, even some people in Phoenix today, people who are homeless, people who are very poor, on the margins, aren't able to afford as much air conditioning as they would like. Okay, so just to sort of give you an overall view again of what we're doing, we take the historical data, we put it in this DLNM from Gasparini, and it gives us the relationship between temperature and mortality. Then we take climate model runs. We're taking this Cordex NA, which, if you're not familiar with that, it's basically high resolution downscaled CMIP6 data using an RCP85 scenario. Doesn't really matter, as I'll explain in a second, which scenario we use. We also take SSP5 population demographics that goes with the RCP85 scenarios, and we plug the climate model into the temperature mortality relationship that we got from the historical data. And this allows us to predict future mortality. Okay, so let's go back to Ramaswamy's claims and make sure we kind of know what are the things we're going to be thinking about. So he made a couple claims. Number one, more people die from cold than heat. So that's one claim that we can now evaluate by looking at historic data. And the other one, which doesn't really say, but is clearly implied, is that global warming is actually going to save lives. And so let's take a look at that. And before we do, though, let me show you a plot. This is out of Gasparini's 2015 Lancet paper, which is really sort of a classic paper in temperature mortality work at this point. And it shows London. And if you look at the top here, this is the relative risk curve, the RR curve, and this is the MMT right here. This line here is the temperature at which the minimum number of deaths occur. And then we split, this is just a definition, any mortality occurring on this side of the MMT are hot deaths. And any mortality occurring on this side of the MMT are considered to be cold deaths. Now, again, remember, a lot of these deaths are happening at 15 Celsius. So I should say this histogram down here is a histogram of the number of mortality, number of people dying at each temperature. You can think of it as a proxy of the actual temperature distribution. But you see that most of the deaths are occurring at temperatures, 10, 15 Celsius that nobody would consider to be cold. And again, this is just a statistical excess death metric. Now the thing that's interesting about this is that cold deaths do dominate. So in that sense, what Ramaswamy said is right. If you take a city like London, you do actually get many more deaths from cold temperatures than hot temperatures. Again, because of the way we've defined cold deaths as any death occurring below the MMT, even though most of these deaths are not occurring at temperatures people consider to be cold. But I think the reason this is a reasonable definition is cold deaths are the ones that as the climate warms, we expect these to go down, whereas hot deaths are ones we expect to go up as the climate warms. So that's why splitting it at the MMT does make more sense. So the question is, this is today. So today, cold deaths in many cities, not all cities, many cities do dominate. But the question is, what about the future? So so in this plot, what I've done, if I may sort of flip back and forth, I've shifted over. It's kind of hard for me to flip back and forth. I've shifted this temperature distribution. Again, this is a death distribution, but think of it as a proxy of temperatures. And I've shifted it over 5 degrees. 5 degrees is about what you get with 3 degrees of global warming. 5 degrees in London is about 3 degrees of global warming. And you'll notice, then this is where it comes into play. This is very steep. And as you push the temperature distribution over, because this is so steep, you're going to very quickly get a lot more heat-related deaths. On the other hand, this cold side is very shallow, which means that as you warm, you actually don't save that many deaths. And so what ends up happening is small climate change will net save lives. But as the climate change gets larger and larger, you eventually get to a point where the steepness of the RR curve on the hot side, the fact that you get many more deaths per degree of warming on the hot side than you save on the cold side, eventually will overwhelm it. So with enough climate change, you eventually will get more deaths. And so then the question is, where is that turnover point? And the short answer depends on where you are. So let me show you Bangkok. So there are a lot of cities, particular cities that are in the tropics, that don't have really big temperature swings, that are kind of optimally adapted to the MMT. So you'll notice that in this case, the maximum number of deaths is right at the MMT, because that really is the temperature they get most frequently. And in this case, any warming at all is going to increase the number of deaths. Okay, so what about our results? So we looked, it's importantly, let me just sort of emphasize this, we looked just at the US. And if you look just at the US, what you see on this plot is the x-axis is global warming. This dashed line is where we are now. We're at about 1.2 degrees above pre-industrial. So this is global warming above the middle of the 19th century. Again, we're at about 1.2 degrees. The y-axis is deaths per year from temperature-related mortality in these 106 cities. The 106 cities are about 65% of the total US population. So if you just kind of scale that, if you want to scale this up naively to total US population, kind of multiply by 1.3 or something, or 1.5. So 3 degrees is about what we're on track for 2100. So we predict a very large increase in temperature-related mortality if we do end up hitting 3 degrees of global warming. Hopefully we won't. We still control how much warming there is over the century, but in the sad case that we don't do anything, this is probably about where we're going to end up. And you also see the impact of adaptation. So these two lines, this blue line is our no adaptation case, and the orange line is the adaptation case, where cities kind of evolve to match using the analog city approach that I talked about before. All right, so what are the things that drive this? So there are really 3 things that are happening that are driving this increase. The first one is population. So as population increases, everything else being equal, if population doubles, you expect deaths per year to double. You expect it just to proportionally increase if everything else stays the same. So that's clearly one factor. Demographics is another factor. Older people are far more susceptible to temperature-related mortality than younger people. We expect a lot of these places, a lot of cities, to get much older. And that's actually also driving a big part of this. And the last one, of course, is climate change. We're getting to higher temperatures. And so you might be saving some lives in the cold end, but you're losing more lives on the hot end. And it's the net of those two that has an effect. Now, it turns out that the biggest impact is demographics. In fact, demographics is responsible for 80% of the increase in mortality, just people getting older. I have one plot to kind of show you this. This shows you the average of the 106 cities. And again, the red curve is older population. The blue curve is younger population. You can see, even though older people over 75 make up just, it's either somewhere between 5 and 10% of the population, they're responsible for the vast majority of temperature-related deaths. So it's really important to understand the impacts of demographic shifts in driving temperature-related mortality. And in fact, you can see, people kind of understand that there's an emerging understanding that this is a problem. Here's a headline from the New York Times: "For Europe's older population, heat is the new COVID." All right, what about climate change? So this plot shows total change in U.S. mortality just due to climate change. And you'll notice that it brackets zero. So numbers above zero are lives net lost. Numbers below zero are lives net saved. What you see is that for this scenario where we adapt effectively, actually, let me say a little differently. So up until about 3 degrees of warming, overall, under any scenarios, we're basically climate change isn't killing more people. In fact, climate change is saving lives. Above about 3 degrees, it depends on what our scenario is, how well we adapt. If we adapt well, we could save lives from just temperatures all the way out to as much warming as we think we're going to get. I think it's unlikely we'll hit 3.5 or 4 degrees of global warming, although it could happen. But if we don't adapt well, then your number of lives lost because of temperature goes up. And so the important conclusions, the first one is keeping warming low is important. You want to keep warming to 2 degrees. That'd be great. Then you really don't have to worry a huge amount about temperature-related deaths in the U.S. The other one is adaptation is important, especially if we don't keep the warming low. And then one other thing, which I didn't put down, but kind of is related to this last question is, let me just emphasize, this is just for the U.S. The U.S., it's the richest country, or one of the richest countries. We've invested enormous amounts in air conditioning, places like Houston and Phoenix. And so we are the most prepared to handle these temperatures. If you go to other places, it is going to be a different story. We haven't investigated that in this paper, but other people have looked at this, and they see that the places in the tropics are going to really be hammered and see very large increases in mortality because of climate change. So let's look at how they're distributed within the US. So this is a plot for Seattle. And you'll notice that for Seattle, when you get above about 2 degrees of warming, you see a pretty rapid increase in number of deaths per year, even for the case where we adapt. Whereas if you go to a place like San Antonio, you'll see that climate change is good regardless of level of adaptation. Climate change saves lives in San Antonio. And so the rule you get is that places that are badly adapted to heat today will do poorly in the future. Places that are well adapted to heat today will do well in the future, because places that are well adapted to heat today, you still see people dying at cold temperatures. And as the climate warms, you will save lives there. But you don't lose that many at hotter temperatures because they're well adapted to heat. Whereas if you go to a place like Seattle, they're well adapted to cold today, so they don't save that many lives from warmer temperatures, but they're not well adapted to heat and will do poorly in the future. And so one way to think about climate change is it's shifting mortality. Even if you say there's not going to be a huge increase in number of deaths in the US, it's shifting it from the southern US to the northern US. Now, economists will tell you that grandmothers are fungible. So if you kill a grandmother in Chicago, but save one in Phoenix, everybody's okay with that. I'm joking, of course. You grandmothers are not fungible. And so this is a real issue. So you can look at it and you say there's not going to be a big impact on mortality, but at sort of the individual level, there still is going to be a big impact, especially for people who live in the northern parts of the U.S. So that kind of wraps up what we worked on. And so I thought I'd talk a little bit about sort of next steps. So these are the kinds of things that I would love to work on with people in this project, if people are interested. And so the first thing to do would be to look at more recent data. So there are data sets that are more recent, that actually go up to present day. You can get them from either Social Security or Medicare or something like that, but you have to purchase them. And it's about $1,000 a year. So it would take 20K to buy the data. I don't have any money to support this. We did this with just sort of other funds, all the preliminary work. So I can't pay for it. You also need to do an IRB, but my understanding is that there are a lot of people on campus who know how to do that. And so I think that would be really interesting. I think there are lots of things you could do if you got more recent data. For example, you can actually look at adaptation. You can look at how the risk ratio curve evolves in time, things like that, which I think would be really good. I'd also like to analyze international data. I actually have not done a lot of work on where those data are located. I know there are data sets out there because other people have analyzed them. And so I think that's something that would be good to do. The other thing I think is useful is that I haven't talked too much about the analytic techniques that we use, this NLDM, nonlinear lagged model. And it's not bad. It seems to work. Everybody uses it. But I think there's actually machine learning would be a better way to do it that might be a little cleaner than it's the conventional way is really quite complicated. So I'd love to try to use a machine learning technique to do it. And lastly, everything is so far has been done just using daily average temperatures. But we also know that people react differently to the maximum daytime temperature and the minimum daytime temperature. So I think it'd be useful if you develop new analytic techniques to also include new metrics in there. So I think there's a lot of work to be done on this. If people are interested, it's something that I'd be happy to collaborate with other people on if people are interested in doing things like this. So let me summarize with these two quotes. So the first one, when Joe Biden says that the number one weather-related killer is heat, what he's talking about is just actual cause of death. So if someone comes in the emergency room with a core temperature of 108 degrees and they die, the death certificates actually say, the death was heat related. And if that's how you determine heat and cold related deaths, you get that heat is the biggest killer. Now, what I showed you in my analysis is this statistical method where we're not looking at cause of death at all. We're just looking at the number of deaths as a function of temperature and looking at how many more deaths we see at each temperature than we do at the optimal temperature. And that's a statistical method. And so that actually does show indeed that more people die from cold temperatures in the US as warm ones. But what's wrong about the quote that's on the right is the implication that climate change is going to save lives. Small amounts of climate change may, but large amounts will definitely not do that. And so let me summarize sort of the main points of this. In the U.S., global warming will reduce total temperature-related mortality below about 3 degrees Celsius. Above that, it depends on adaptation. But even if there's little change in total mortality, it's going to redistribute mortality when we move to higher latitudes. And the U.S. is rich and already well adapted. Other places are going to do much worse. Anyway, so that's all I have. I'm happy to answer questions.
Thank you. So Andrew, if you can open up the chat box, I think there are some comments from the team. This has been really interesting. It's my second time hearing, but I still learn new things. So I think I have some comments from Justin and Tara. Do you want to unmute? Maybe ask your questions.
Yeah, I can also see their questions. I could just go through, I can just go through them if you want.
Yeah,
Um,
please go ahead.
so certainly somebody knows. So Tara asked a question: do we know the causes of these? So the short answer is somebody knows the causes of them. In this analysis, we don't look at that. So all we're looking at is the total number of non-accident deaths. So in fact, vehicles and falls would be excluded because they're not because these are not accidental deaths, but they're any kind of sort of natural cause type deaths. My guess is there might be a spring rainy season flash floods. I'm not sure what that refers to. Justin, do you want to expand on that?
Wait, sorry, before you, I just want to ask a follow-up to your response about
Sure.
that. I mean, to me, that's a big data challenge, though, is if you're saying that vehicles and falls are accident. I mean, and I know that's how they're characterized, this idea of accidental deaths, but it's like, but if someone drives off the road because it's icy conditions, and we're talking about trying to quantify like weather effects on that, or falls on slippery, and I mean, 60 degrees Fahrenheit is not icy conditions or whatever, but I just as an example. So to me, that I don't know. I'm kind of curious about your thoughts on like that as just as a data issue.
Yeah, I mean, I guess the big picture data issue thing is that data is really the challenge on all of these things. It's getting the data, it's interpreting the data. I don't have anything to back this up, but my guess is that going off the road in icy conditions is probably not that many people. But it's a good point, and I don't really have a good a lot of what we did. I told Jang Ho, I said, look at what other people did and do the same thing, because that's the way you get stuff through peer review. You just you take the assumptions that everyone else made and you make the same assumptions. And so we basically followed what other people had done. The thing that I think was really new in our analysis was our methodology for adaptation, which was unique, and sort of our focus on US using the Cordex data, using the Cordex climate model data to really split out demographics, population, and climate, which also hadn't really been done in an effective way. So yeah, I mean, this is an issue not just with our paper, but I think with everybody's work.
Sure. One just really quick, sorry, Justin, just really quick follow up on that. So like for Storm Uri, where multiple people died because they were running their car in the garage trying to get warm and they died from that, is that then characterized as weather related or not flagged as?
Well, so our data didn't cover Uri. So
just as an example of like that
I honestly don't know how they would categorize that. That probably sounds to me like it would be categorized as accidental and not included as weather related. But you're right, that probably should be related. I mean, almost anything that happened during Uri, that is a case where driving off the road probably was a significant, driving off the road, carbon monoxide poisoning, all of those things probably should be counted.
Thank you.
I guess to follow up on that point, because I think in urban planning, we have an issue with the word accident, right? Accident, it means like, oh, it was accidental, but maybe a more technical word is the word crashes, right? And so I would think, I guess my question, I was asking the question really about, you asked about 15 degrees and why 15 degrees, might there be a spike? I was thinking about it in terms of, well, people are in their air-conditioned cars and air-conditioned buildings, and they're driving around. I could see definitely to Tara's point, the ice would make them increase deaths. And I can see if somehow their air conditioning wasn't working, that would lead to deaths. And then I could also see if there was precipitation events, like it's raining, it's a monsoon season or whatever, that could lead to deaths. But to me, those are all weather related and temperature related as well. And so that question really was about that. And so I would be really interested in the study including all the accidents in it. Because I do think those are weather related, whether they're categorized as that or not.
Yeah, I'll tell you, that's actually a great suggestion, which is to do, because if you look at the sort of the standard Gasparini method, they basically take out the seasonal cycle of, the first thing they do is they take out the seasonal cycle, and they're just looking at short-term variations in temperature, basically, over the last like 20 days. But it would be really interesting to do a seasonal analysis to look at that seasonally. And I don't know that anybody's done that. I mean, that's actually be quite a good, and shouldn't be a very hard research project, just to figure out how do these things vary, throughout the year.
Right. And I guess while I'm already here, I had the question later in the chat. I was curious when you said adapted versus not adapted well, how we're defining that. What does that actually mean practically?
Well, I mean, what I mean by that is, a well-adapted house in Seattle today might be one that, you could be well-adapted, not have air conditioning if you have really good insulation and, shades on your windows, things like that. But in the future, to be well-adapted, you'll have to have air conditioning. And, in our paper, we had these two assumptions, one where the relative risk curve stayed exactly the same at all temperatures, and the other one where we use the analog city approach. And so we use that as our assumption. I mean, nobody really knows what adaptation is going to look like. My opinion is adaptation is going to be really very ineffective. Just kind of look around the world today, and you don't see people adapting well to climate change because it's going to be so expensive. People are just, adaptation is going to require rich people to pay to help poor people adapt, and we know they're not going to do that. So, so I think it depends on, the context, but you have to define what adaptation is, and there's no, I think, specific definition.
I just want to jump in, Justin. I think that was a great question, and I want to follow up. And Andrew, thank you very much. I think this is a very, very interesting study, and it's really something very helpful to think on. I was thinking for the adaptation, before you mentioned about the AC and the air conditioning availability, if it is related to our bodies and how we adapt to the environment, and for instance, like if someone is used to live in a more colder environment, and then when they travel to a more warmer environment and they started to get exposed to more really high temperatures, what does that mean? Or the other way around. So I was wondering if we, for instance, increase the air conditioning more in places, are we also causing them to be less adaptable to other places? So I'm not sure if that makes sense, but I was wondering if we are doing anything related to our own body adaptation, and if there's anything that needs to be done from that perspective when we talk about adaptation.
Yeah, no, I mean, I think that's a good point. Clearly, people do adapt, and that if you spend a lot of time in cold weather, you're more capable of handling colder temperatures, and things happen for warm weather. And it's probably the case that your body doesn't adapt as well if you're living in a really well adapted environment. In general, that should be included in the observed mortality data. So that is to some extent already included in there, to some extent already. So I think that's, is it done? Is it in the future analysis? How well is that done? I think that it is probably captured in our high adaptation scenario.
Right. Thank you very much. And one other thing, this is more a clarification, Andrew, I would like to ask. So when you first started, I think it's a powerful sentence, like the number of deaths due to weather is far exceeding the deaths from other events like flooding or tornadoes. This is not an area that I know well, but I think those events are also happening because of the climate change, or there's an impact of climate change, or there's an impact of heat, or the change in temperature. So without knowing exactly the actual cause of death, which seems to be one of the most important next steps, I guess. But I'm a behavior scientist, so maybe that's why my focus is more on what is happening and why it is happening. Do you see that there will be benefits to start maybe looking into other data sets, not really focusing on the heat, but trying to merge different data sources and different data sets and see like if there's a way to understand better the cause of that, or if it is going to be too expensive and too infeasible or too unrealistic to do that for the next research agenda.
Yeah, no, let me break that down. So first, certainly you're 100% right. Climate change affects all weather events. We know that it's making hurricanes more destructive. It's increasing the rainfall from hurricanes. It's raising sea level, which makes storm surge for hurricanes worse. It's also generally making intense precipitation events worse, which is increasing flooding. So it's and temperature increases drought. So it affects all of these things. So there's no question that some of the deaths associated with all of these things can probably be tied to climate change in some way, or at least most of them. Things like tornadoes, I don't think we actually have a good handle on how climate change is going to change those, although I think you might be able to make a plausible case that we're going to get more tornadoes. As far as looking at deaths from disasters, I think that the important thing is you need to have enough deaths that you can do some kind of statistical analysis. With temperature, a lot of people die. Everyone dies at some temperature. So you've got a lot of data you can put into your regression. I don't know for these other things you can do it. I mean, clearly someone mentioned Uri. You can take Uri and you can look at the excess deaths and you can see, 1,000 people died during Uri. I mean, I actually did that calculation myself. I downloaded the mortality and you can, it's like 1,000. It's a lot more than the official number of reported deaths. So for some things, I think you can do if enough people die, but it's going to be hard. Like we just had this big tornado outbreak a few weeks ago, 2 weeks ago. And, people did die, but not that many. It's amazing how few people die for these things. It goes to show you how kind of well prepared, the warnings that people get really are effective. But I think it's not a bad idea. We should continue thinking about that, see if we can come up with a good hypothesis.
Thank you very much, Pam.
Sorry, do you want to continue on with the chat box
Oh,
comments?
sure. See here. So here's a question from Tara. 2023 study looking at hot conditions increased VMT.
Vehicle miles traveled, driving.
Oh, I see.
Driving.
Yeah, that was just a study I found I wanted the team to see because it backed up your point about how people with the money will be able to flee or do other things,
Yeah.
on the day-to-day or the longer term versus other
Right.
folks who don't
Yeah.
have the option.
Yeah. And then Ji-Woon said, I would be interested in seeing other meteorological variables. Yeah, no, I think that's a very good idea. I would love to do that. If right now I'm really limited by support. I had a student, Zhang Ho, who was really interested in this stuff, and I had a little extra money, but he's graduated. And so, this is the kind of thing that I need to write into a proposal or do something. So I'd be happy to collaborate with people that are also interested or do something to get some funding to look into these things. I have two quick questions from Dong Yang. Some studies use air temperature while others define a threshold. I wonder how you consider this. So we did what everybody else does in these kinds of studies, which is use temperature as just a continuous variable in the regression. I don't know, given the shape of the curve, I don't know if using a threshold is a great idea. I'd have to think about that some more. Next question, Justin, how are we defining adapting or not adapting? I think I talked about that already. Tara, do we have good numbers on what percentage of people don't have AC at home or poor AC? So there is data on that. So there's something which I'm sure you guys know more about than I do, like America's Community Survey, I think that's what it's called. And I haven't actually looked at it, but they do. That's one of the things I've thought about doing. The other thing is, places like Zillow or CoreLogic, they have data that also has air conditioning. I've been talking to people in the real estate group here about getting those data to sort of do this kind of study. I think that's a 100% agree. AC, what's happening, it's really interesting. What's happening with air conditioning is it's gone from a privilege to actually being something you need to have, like running water. I mean, if your air conditioning goes out in August in College Station, I don't think you can live at home. I think you've got to go to a hotel, or I mean, assuming you have the money. And if you don't have the money, then I guess you go to a neighbor's, or worst case, you gut it out. And if you're old or weak, it's going to kill you. And I was just looking at a paper today about what happens if there's a blackout during a heat wave. And I've often thought that's kind of the worst case scenario. So
I
anyway,
think, it gets. Oh, sorry, go ahead.
I was gonna say, man, you also mentioned manufacturing housing. That's also a real key thing. Manufacturing housing is often the worst insulated housing, and the people who live there have the least amount of money. And so, yeah.
I just think it was to Justin's point about like how are you defining well adapted larger, because you could say like, oh, San Antonio, there's like more AC than in Portland where I lived, and in places there's no AC, but at the same time there's like huge swaths even in the places like San Antonio or anywhere in Texas where there's these groups of people who aren't well adapted. So I think it's kind of how we define well adapted, and then also what that means for planning, because I know Tucson, I think it's the city of Tucson, right? Is it Phoenix or Tucson just came out with their heat, like they've got big heat protocols going on. They're doing a lot with urban heat and this issue of like cooling centers. So if you don't have good AC and you don't have the money to go stay in a hotel, but like, what kind of planning are they doing for 24-hour cooling centers versus just like daytime cooling centers and all that?
Right.
So.
Yeah, no, there was, Phoenix is a really good case because, it's probably, one of the most adapted cities, and yet they still get a lot of heat deaths because of exactly what you said, which is that there are homeless people. Homeless people don't have air conditioning. There are people who have air conditioning but can't afford to run it because it's just so expensive. And so I 100% agree that, even in these places that are well adapted, there are going to be people that are suffering. In Phoenix, I can't understand why anybody is moving to Phoenix now. I mean, it's doomed. Phoenix and New Orleans, I'm just shocked that anybody lives in those places now. I guess they're gonna learn the hard way. And as far as cooling centers go, I'll tell you one thing I've realized is I've talked to a bunch of city heat people. Every big city in the South has like a heat person, and they all have cooling centers, but none of them have a plan for what to do if the power goes out. These cooling centers often are libraries or things like that don't have backup power. And so then the question is, what are you going to do? It's going to happen. It's going to be very bad.
I want to chime in here real quick. Just an interesting point. I do, one of my volunteer things I do is I visit people who can't pay bills. Either they can't pay rent or they can't pay utilities. And I sit with them and I talk with them about how to help. I do that through St. Vincent de Paul here in town. Really interesting here in College Station. During the summer, it's like people who are lower income get hit two ways. First way is everyone's out for the summer. So all service jobs, if you're working restaurants, clean rooms, their hours get cut. And so they're not making revenue. And then it's so hot that utility bills are off the roof. And so we get tons of calls of people who can't make bills meet because of both the revenue, because of being a college town, and then because of heat with utility bills. So that's a thing that goes on here in town. If you guys don't know about it, so.
Yeah, and the utilities here will cut you off very quickly. I was shocked at how fast you get cut off from your electricity if you don't pay your bill. It's like 2 months or something. Like, I think if you miss 2 bills, I mean, there's no forgiveness or understanding that these things are life sustaining. Air conditioning is, you need it to I mean, you really need it to survive at this point. And I think
I think there is a policy here in town anyways, where they can't cut you off if the temperatures reach a certain height. But then they just, it just adds to your bill that you get further and further behind, so.
Any other questions?
Yeah, I'll tell you, I actually have to go. I have something else at 2, so I can be a few
Okay.
minutes late.
Andrew,
But yeah, let me just say, if anyone's interested in doing more work on this, I'm really interested in it. I'm interested in sort of all of these aspects. So, you know, I have a good, I'm the guy who has all the climate data you can imagine. So, you know, if you need, if you have other data sets that you want to combine with climate data, let me know. We have every imaginable set of data on the physical climate systems. Just let me know. Anyway, thank you guys.
And we'll follow up, Andrew. I think there might be some interest in doing some follow-up work with you, so.
That'd be great. I'd love to chat with people. All right.
All right.
Bye.
Thank you. Appreciate it.
Thank you.
Thank you.